Hi everyone, this is Miss Privet, and I am going to do a short little lecture on atomic structure. So you can hopefully see on your screen the notes. Get out a notebook and or a place to take notes and come join me on this. So this is a little introduction to atomic structure. So we have been learning about the history of the atom, and while we have learned about protons, neutrons, and electrons, we have not gone into kind of the nitty-gritty, the details of these particles, and so we're going to just kind of summarize those and some of the ideas that we've been studying. So it's important to note that electrical phenomena, like when you experience static electricity or there's a lightning bolt or the lights turn on, all of that electrical phenomena, that's a fundamental property of matter, electrical charge, meaning, said another way, we are composed of atoms, and all matter is composed of atoms, and those atoms are composed of charged subatomic particles. So literally everything that makes up the world around you, my entire room, this stylus, the computer screen, your body, an apple, everything is made up of atoms, and those atoms are made up of those subatomic particles which have charges. And so the world around us is charged, and we can see that phenomena happening in the world around us, and it has macroscopic events that happen to us, but at the atomic level, which is the submicroscopic level, so smaller than a microscope, there are things that are causing those charges to happen, because simply put, atoms are made up of subatomic particles. So here we have this chart, which I want us to kind of fill in so that we can have a little bit more detail about protons, neutrons, and electrons. And this is going to springboard the next kind of half of the unit. So we've done the atomic history, and now we're going to dive deep into the atomic structure and make sure we really know the different symbols and forms of these particles. So let's start with, let's keep it positive and start with the proton here and kind of fill it out. It's easiest if you just kind of like, you know, kind of write as you go. You don't need to decide like the spacing on this. But you've got the proton has a 1 positive charge, meaning every proton has a 1 positive charge. So if you had 2 protons, you'd have 2 positive. If you had 100 protons, you'd have 100 positive. Okay, each one is 1 positive charge. A shorthand abbreviation for proton is P positive. Protons are located in the nucleus. And relative AMU, relative mass, okay, so the mass of a proton is like 1 proton is really, really small, okay, so like on the tip of a needle, not even the stylus, there's over 200 million atoms. So, and that's the whole atom, that's not even like the protons. So we're not talking about the actual mass of a proton. The actual mass of a proton is somewhere on the scale of 1.7 times 10 to the negative 27th kilograms. So really, 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 really small. But the relative mass, and it's called an atomic mass unit, AMU. So it's comparing those particles at that level to each other, is 1 AMU. And the proton is relatively a heavy subatomic particle. The next subatomic particle let's talk about is the neutron. That has no charge, and it gets the symbol N with a little 0. It's also located in the nucleus. It also has a relative mass of 1 AMU, so it's also relatively heavy. The last subatomic particle is that beautiful electron, which is actually what we'll study a lot this semester. It has a charge equal and opposite to a proton, so it's 1 negative. It gets the symbol E negative, and it's located outside the nucleus or around. And its relative mass is 1/1836 AMU, meaning you would have to have over 1,800 electrons to make the mass of 1 proton. So we say that they are essentially massless, or they're very light. So these are the heavy subatomic particles, and they make up most of the mass, essentially all of the mass. We say make up all of the mass of the atom. And, but the electrons occupy the volume, the space around. And so if we kind of draw and label this, so if we were to have our protons, and let's just put 2 and 2, this would be a helium atom, since you'd have 2 protons and 2 neutrons. That would be a very stable helium atom. I'm gonna make it really small since the nucleus is supposed to be really small. And then you'd have these electrons, you know, out here. They're not really that big, but like I'm gonna do these little dashes, not because like there's more than 2 electrons, but because like the space and where those electrons are is a much larger space. That's what I mean by the volume. So like the nucleus is this tiny little center, and it's where, you know, the mass is. The nucleus is the heavy mass center of the atom. And then, but if you were to take like the whole space of the atom, most of it, like the rest of it, you know, got this tiny little pinpoint in the middle that is where the protons and the neutrons are. But then you have these electrons which are occupying most of the space. And so it's kind of fun, like actually like 99.99% of the atom is empty space, because these electrons are just like moving around randomly. And then you've got the nucleus, which also you should know is extremely stable. So the nucleus is stable, 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 okay? That's not going to change. It's very hard to change the nucleus. And so when we talk about changing things about an atom, we actually change the electrons, and they're really the rock stars of the story in chemistry, because they're so light, right? They weigh essentially nothing. If you inject them with energy, they can move and they can be removed and they can be added, and all of those things do stuff to the macroscopic world that we experience. And so changing the charge of an atom is by changing electrons, because you can't really change the nucleus. The nucleus is very, very stable, and it's not going to change, okay? So it's important to note that the nucleus is stable, and that changing that requires nuclear chemistry. So either nuclear fission or fusion, and that takes a whole lot of energy, and we don't really see that every day in our day-to-day world. So even like a lightning bolt is not changing the nuclei of atoms. So just to kind of give you like a really good picture of the atom. A key idea here that you need to bold, star, highlight in your notes is that all atoms are neutral. All atoms are neutral by definition. Now, can you have stuff that is not neutral? Yep, but it's not an atom. So if you're talking about atoms, you're talking about a neutral atom. And then what that means is that the number of protons is equal to the number of electrons, meaning if you have 2 positive charges, you have to have 2 negative to balance them out. If I had a third and I only had 2 electrons, that wouldn't be balanced. While that is a thing, that would not be an atom. That would be something called an ion, which we will cover later, just not today. We're covering atoms. So in order for an atom to be neutral, you'd have to have the same amount, which means if we know what atom it is and we know how many protons there are, we then therefore know how many electrons are, because they have to be equal. So that's going to be a tidbit that's going to lead us kind of into our next topic, which is like, so how do these things get symbolized, and how do we read them on a periodic table? So there are symbols and characters and notations that we have to learn in order to be able to determine how many protons, how many electrons, how many neutrons are there in any one atom. And that is what our next lesson will be on. So this is a little introduction into atomic structure. Hope you enjoyed it, and I'll see you for the next one.